So today we will be finally finishing up our informal look at the implications of the de Broglie hypothesis. In particular, we've been discussing Bohr-Sommerfeld quantization. And last time we had completed our derivation of the hydrogen atom, and we were in the middle really of exploring the behaviors of our solution through something known as the correspondence principle, which we will discuss in depth today. After that, we will move to our second worked example of Bohr-Sommerfeld quantization, in particular looking at the simple harmonic oscillator, as I like to abbreviate SHO. And then, time permitting, we will be moving on to begin to look at building a formal theory after having seen how well at least this de Broglie hypothesis can at least semi-quantitatively predict behaviors. Now, a few key facts we're going to need to know from last time. So last time we were analyzing the hydrogen atom within Bohr-Sommerfeld. And just a quick overview, we had written down the Hamiltonian, which numerically equals the energy for this system, as the kinetic plus the potential energy, where we simply have a proton and a hydrogen atom, so this is our Coulomb potential. We then applied Newtonian mechanics, in particular using Newton's law F equals ma, which very quickly led us to the virial theorem. And everything after this point actually only depends on this fact about the balance between potential and kinetic energy in an orbit. So if we have some more fundamental reasons to really believe in the virial theorem, beyond just pure classical mechanics, you could use that or faith in this particular result to build even stronger confidence in the Bohr-Sommerfeld condition. And this, in fact, is one of the reasons why we ended up actually with exact results. Now, from this virial theorem immediately follows that the kinetic energy equals minus the energy, and we can then relate that directly to its definition. Likewise, the potential energy actually equals twice the total energy. And then from these two relations, we can quickly solve for the momentum in terms of the energy and the radius in terms of the energy. We then also looked at the basic Bohr-Sommerfeld condition. We evaluated what that would mean for a circular orbit, and then inserting our result for momentum and position in terms of energy, we were then quickly able to solve for the energy of these discrete levels within hydrogen, where the quantum number, that's what n is usually referred to as, so I'll write that down, where the quantum number in this case is taking values n equals 1, 2, 3, etc. We have a nice result for the energy in terms of the quantum number and also for the radius in terms of the quantum number. We then considered two classical limits. One is where we take h bar goes to 0 and then ask what happens to the radii of the first orbit and its energy. And what we found then was sort of the expected behavior, which is that, well, as quantum mechanics goes away and we have pure classical mechanics, the way this system naturally minimizes its energy is for the radius to go to 0 so that the electron sits right on top of the proton, which then would give us a negative infinite potential energy. We were actually looking at this finally from a more subtle point of view. In particular, we were considering the limit when Planck's constant vanishes while we keep this product n times h bar constant. The motivation for that is you will notice that the energy and the radius of the orbit all just depend on this one factor n squared h bar squared, which is really just the square of n times h bar. So if we could keep n times h bar constant while making the limit h bar goes to 0, that would then keep the radius of the orbit constant and its energy. So what we would then be looking at is basically we could take some fixed size orbit and slowly turn off quantum mechanics, letting h bar go to 0, and then having no quantum mechanics, but maintaining the radius of that orbit, and we should thereby be able to recover classical physics. Now, this kind of a limit at first sight can be a little confusing, but just notice what we're doing is we're just taking the limit that Planck's constant vanishes, and while we take that limit, we define n to be whatever this constant value is divided by h bar. So as h bar is vanishing, the quantum number n will be heading towards infinity. And then we asked, if we did have such a system, what do we know should happen from the classical physics point of view? Well, from classical physics, we know that the electron actually, as it oscillates around the atom or goes in this circular orbit, creates a changing dipole moment, which will then radiate away energy slowly. At some frequency, and that frequency is actually determined by 1 over the period of the orbit. That's a classical electromagnetic theory. And then, as that energy is radiating away, it must be coming from somewhere, and where that energy ultimately comes from is the orbital energy of the electron, which then decreases as the electron therefore then slowly spirals into the nucleus. So the question is whether or not all of this beautiful classical physics is somehow buried in our quantum mechanical results. So what we want to do is to think about what this system in this limit should look like quantum mechanically and what that quantum mechanical behavior would be. And then we want to see whether or not that quantum behavior corresponds precisely to this classical picture or not. And here's how we can do that. So if we take this quantum view, what we know from the quantum view, and again, this is going to be in this limit that h bar goes to 0. In the quantum view, you again have your proton in the center, and you have your electron outside in these circular orbits, but now the circular orbits have discrete values associated with them. It has a certain radius Rn and a certain energy E sub n. And as h bar goes to 0, you can see that the spacing between these orbits will get closer and closer because n is going to be some very large number as h bar vanishes. And if n is a large number, whether we're looking at 1,000,000 squared or 1,000,001 squared doesn't really change that radius very much. So there's going to be a whole series of these closely spaced orbits. They're not spiraling. It stays in these discrete orbits of these various different sizes. So this here would be the radius for the n-1 quantum number and E sub n-1. Now, if we consider from our quantum view what would happen to an electron, say, in this outermost orbit, once again, working from the general physical principle that systems, generally speaking, eventually will find some way to couple to their environment and give off any excess energy and then try to move down to lower and lower energy states, we would expect that after a while this electron in this outermost orbit would give away some energy and make a transition down to, say, this next orbit. And the energy associated with that change, right, as we've seen, should correspond, the energy differences between the energy levels generally then corresponds to the emission of some electromagnetic radiation, namely a photon. So we expect then photons to come out from these transitions with an energy equal to h nu, of course, would give me the frequency associated with this photon, but the specific energy that we're expecting is delta E, where delta E is just the energy difference between the successive orbital levels. So the big question is going to be whether or not then this picture aligns with the classical view. And already we can see a very close correspondence. The first thing, as we had said, is these orbits are very close together in radii, and therefore they should be close together in energy, which means even though we're making these various discrete jumps from the outside classical point of view, as quantum mechanics gets turned off, it would appear more like a continuous loss of energy so that it would look like something that's spiraling inwards. So the question is whether or not that actually begins to occur. So do we get, is going to be the big question, two key things that we need to see. One, we need to see that delta E goes to 0. These are things do we get as H goes to 0. Is this change in energy getting smaller and smaller so that it really would look more like a continuous spiraling inward as we hop down from one orbit to the next. And the second thing is whether or not the radiation here comes out at precisely the correct frequencies. What we want to happen is that this delta E which will then tell us the frequency of the photons coming out, we are really hoping that that will correspond to h times 1 over, well, the frequency coming out here is 1 over the classical period. I'll call it T sub CL. So the question then is, will the quantum changes in energy equal h over the classical period? And while we are at this, we should determine what that classical period is, where the classical period is equal to, well, in the classical view, and so that's our second question here, of course, and in the classical view, the period would be the total distance traveled around one orbit divided by the velocity. So classical period would be 2 pi r divided by the velocity, but velocity we know is actually momentum divided by mass. And so the energy change that we are hoping to see between our orbits is, we're wondering, will delta E actually equal h over this classical period, right? So when I do h divided by this, I get an interesting result, right? I will get h over 2 pi. So I'll have h over 2 pi, which is h bar, which is very nice. Also, when I divide by this quantity, so this 2 pi went in my denominator, my mass m should go in my denominator. And in my numerator, I should have the momentum divided by the radius. So I'll have p divided by r. And the question is whether or not this relationship will hold. If it does, then we have this beautiful result that not only do we have the spiraling in from the classical physics, or corresponding to it, but we also have that we're predicting that the radiation that comes out is the same radiation frequency as in the classical view. So we're completely recovering our classical physics results. So what we will do now is get into a more mathematical discussion to verify whether or not we obtain these two results.